Swayam Prabha. Digital India. Educated India.
Welcome you all again in this lecture. Here we will do initially two theorems. One is the initial value theorem, another one is the final value theorem. And after that we will see what would be the Laplace transform of periodic function and their properties. Initial value theorem and final value theorem means you are using two parameters, one is t, one is s. So, sometimes t can approach 0 or t can approach infinity, similarly s can approach 0 and s can approach infinity. So, what would be the effect on that we will see now. First, let us see the first theorem, that is initial value theorem. This initial value theorem states that let f t be a continuous function for all t greater than equals 0 and be of exponential order as t approaches infinity. And if f dash t is of class A, that is f dash t is maybe piecewise continuous and is of exponential order, then as t approaches 0 f t, this must be equals to limit s approaches infinity s f s. So, basically whenever t is approaching 0, that value for the function f t, this should be equals to the limiting value of s f s whenever s approaches infinity. Let us see the proof first and afterwards we will see what is the use of these particular theorems. Here from the theorem of derivatives, you know this thing, Laplace transform of f dash t, this is equals s f s minus f 0. S f s minus f 0, we know it well, and this I can write down 0 to infinity e power minus s t into f dash t dt. This is equals to s f s minus f 0. This left hand side I am writing from the definition of Laplace transform. Now, if I make s approaches 0 on both sides of the given equation, then I can write down limit s approaches infinity 0 to infinity e power minus s t f dash t dt. This is equals limit s approaches infinity f s minus f 0, because this is independent of s. Or this I can again write down limiting value of s approaches infinity s f s. This is equals f 0 plus limit s approaches infinity, limit s approaches infinity 0 to infinity e power minus s t into f dash t dt. This is equals to, you can write down f 0 plus 0 to infinity. This limit s approaches infinity you can bring inside this, so that it becomes limit s approaches infinity e power minus s t into f dash t dt. And what is this limiting value? So, what you are getting, limit s approaches infinity s f s, this is equals f 0, because this value if this is equals f 0 and this limiting value will approach 0, because the limit s approaches infinity e power minus s t will become 0, and this f 0 we can write down limit t approaches 0 f t. This I can write it like this, limit t approaches 0 f t. So, that our proof is complete, that limit t approaches 0 f t equals limit s approaches infinity s f s. So, please note this thing, that if I take a function f t, the limiting value as t approaches 0 always will be equals to the value of the function, limiting value of the function s f s whenever s approaches infinity. So, this is the initial value theorem, the proof whatever I told, that just I have written. So, that making s approaches infinity you are getting this, you will come back to this line and from there f 0 plus limit s approaches infinity e power minus s t in 0 to infinity, which will become 0. So, that you will obtain limit s approaches infinity s f s, this is equals limit t approaches 0 f t, and which you can write down this as f 0. Now, the final value theorem, this is just the opposite one. In the earlier cases you have seen t is approaching 0, s is approaching infinity. Here opposite thing comes. So, again let f t be a continuous function for all t greater than 0 and be of exponential order as t approaches infinity. And if f dash t is of class A, then limit t approaches infinity f t, this is equals limit s approaches 0 s f s. So, limit t approaches infinity f t, this is equals limit s approaches 0 s f s. So, let us see the proof of this one. Again we are starting from the similar thing, that is limit Laplace transform of f dash t, we know it, this is equals to s f s minus f 0. So, that you can write down 0 to infinity e power minus s t into f dash t dt, this is equals to your s f s minus f 0. These two steps are same whatever we did earlier, that is in the earlier case what you did, you made s approaches 0, but in this case we will make s approaches, sorry, in the earlier case you made s approaches infinity, but here we will make s approaches 0, because we have to find out limit s approaches 0 s f s, this equals limit t approaches infinity f t. So, as s approaches 0, we can write it as limit s approaches 0 s f s minus f 0, again this will remain constant. This is equals limit s approaches 0, 0 to infinity e power minus s t into f dash t dt. Now, I can interchange the limit and the integration, so that limit can go inside the integral and you can write down this is equal 0 to infinity limit s approaches 0 e power minus s t into f dash t dt, and this value now it is 1, limit s approaches 0 e power minus s t. So, that this equals, you can simply write down 0 to infinity f dash t dt. So, that it will become f t from 0 to infinity. Now, this is f infinity, that means you can write it limit t approaches infinity f t, the value of the upper limit at t equals infinity minus your f 0. For the lower limit it is f 0. So, f 0 will be cancelled from both side. We can cancel f 0 from the both side and we can write down limit s approaches 0 s f s, this equals limit t approaches infinity f t. So, please note that this completes the proof of the final value theorem, which says that limit t approaches infinity f t, this is equals limit s approaches 0 s f s. So, if we go to quickly this one, we know this from here, we are getting 0 to infinity e power minus s t f dash t dt equals s f s minus f 0. We are making now as s approaches 0 this limiting value. We are putting the limit inside the integration without changing the notation. So, that value is 1, you are getting 0 to infinity f dash t dt, which is nothing but f t at t equals 0 to infinity. So, this if I put the limits, this is limit t approaches infinity f t minus f 0. So, that f t will be cancelled from both sides and you will obtain this. So, this completes the proof of the final value theorem. Now, fundamental theorem on periodic function. If there is a periodic function, what would be the Laplace transform? For that, a generalized function have been generalized theorem has been made. Suppose f t be a periodic function with period t greater than 0, is a periodic function with period t. So, that f u plus n t equals f u, where n can take values 1, 2, 3, etc. So, I am assuming a function s t which has a period t, and you are writing f of u plus n t equals f u, which ensures that the function is a periodic function with period t. In that case, the Laplace transform of that periodic function f t will be equals to 0 to in t e power minus s t f t dt by divided by 1 minus e power minus s into capital T. So, using this formula directly depending upon the value of the periodic function f t and the value of the period capital T, we can tell what will be the Laplace transform of a periodic function. First, let us go through the proof of this. Your Laplace transform of f t, this is equals, you can write down 0 to infinity e power minus s t into f t dt. This you can write it, since it is a periodic function of period t. So, 0 to infinity I can break it into sub interval 0 to 2 t to 2 t like that way. So, 0 to t e power minus s t into f t dt plus t to t 2 t e power minus s t into f t dt plus like this way. I will continue up to nth term, some say n into n to infinity e power minus s t into f t dt. Now, this equals, you can write down 0 to t, if first one will remain unchanged e power minus s t into f t dt plus this I can change this function t to 2 t e power minus s t to t, this I can break it into 0 to t e power minus s into u plus t into f of u plus t du. That is, I am making a substitution, capital T small t equals u plus t. I am making this substitution that u plus capital T equals small t. So, that at t equals 0, if I make t equals u plus capital T. So, the limit at t equals capital T u will be 0, at infinity u will be this t at u equals 2 t, at t equals 2 t u will be equals to t. So, the limiting value is changed to 0 to t, and similarly if I take the third one and substitute the same thing, then third integral would look something like this 0 to t into e power minus s into u plus 2 t into f u plus 2 t into du plus like this way it will go on continuing like this. So, effectively what I am doing, my integrals was from 0 to t, t to 2 t, 2 to 3 t like this way. Each of them using the substitution this, I am converting it into the interval of 0 to t. So, that this equals, now you can write down 0 to t e power minus s t into f t dt. This what will happen? This e power minus s t I can bring it outside. So, that this I can write down e power minus s t into 0 to t e power minus s u into f u du For the second case, I have to bring it e power minus twice s t, I can bring it out. So, e power minus twice s t 0 to t into e power minus s u into f u du, and it will continue like this way. So that from all of them now, if you see, you can take common this integral, that is 0 to t e power minus s u into f u du. This I can take common from the all the integrals. So, this equals, I can write down 1 plus e power minus s t plus e power minus twice s t, like this way it will go on and infinite series will come, and this is equals 0 to t e power minus s u into f u du. So, once I am getting this series I can write it as 1 minus 1 by 1 minus e power minus s t. So, this equals, I can write down in simple way, your integral is there 1 by 1 minus e power minus s t into 0 to t e power minus s u into f u du. Or in other sense, same integral I can write it 0 to t e power minus e power minus s t 0 to t e power minus s u into 0 to t. So, it will be s t into f t dt by 1 minus e power minus s t. So, once I am doing this completes the proof of my theorem over here. So, if you see this, so your Laplace transform, you are breaking it into 0 to t, t to t. Now, using the substitution t equals u plus capital T in second, third and like this all other integrals, you will find that I am getting 0 to t e power minus s t f t dt plus 0 to t e power minus s into u plus t into f of u plus t du. Like this way I am continuing. So, that I can I am putting it like this. So, from here I am just breaking e power minus s t in the second integral outside, e power minus twice s t in the third integral outside. Like this way I will get a series 1 plus e power minus s t e power minus twice s t, and like this. This integral this series is nothing but 1 by 1 minus e power minus s t into 0 to t e power minus s u du, and which I can write down 0 to t e power minus s t into f t dt. Actually, this capital T will be the small t, because here it is small t into f t dt. Now, I am just giving you a list on this, where I have listed the important Laplace transform of different theorems we have written. The first one, just this is a recapitulation whatever we have done earlier. One is the linearity property, that is, if the function is a1 f1 t plus a2 f2 t, then Laplace transform of f t can be written as a1 into Laplace transform of f1 t plus a2 into Laplace transform of f2 t. Laplace transform of e power a t into f t is f of s minus a. If my g t is f of t minus a for t greater than 0 and 0, then Laplace transform of g t is e power minus a s into f s. Laplace transform of f of a t is 1 by a into f of s by a. Similarly, the other one, Laplace transform of t f t and Laplace transform of t to the power n into f t. And here also in this slide, the division of the function by t, which we did. Then we have the integral theorem, that is 0 to t f t f x dx, Laplace transform of this is 1 by s into f s. Then we have written the initial value theorem, which we did just now. We have the final value theorem we have written, and also what is the, if the function f t is a periodic function, then Laplace transform of the periodic function is 0 to t e power minus s t into f t dt by 1 minus e power s t. So, if you just note these two slides, then very easily you can remember what are the theorems we have done and what are the important things we should remember. Now, let us come to some examples. We want to find the Laplace transform of sawtooth wave function. What is sawtooth wave function? Sawtooth wave function is defined as f t equals t whenever t lies between 0 to capital T and it is 0 whenever t less than 0. So, we are saying that sawtooth periodic function is a periodic function with period capital T. So, that if we have written f of t plus capital T, this is equals to f t, and the graph is also given from 0 to capital T, it is taking the f x equals x, t to capital T, it is taking another same graph x, and like that way it is continuing over here. So, that the next is how to find out the Laplace transform of this sawtooth wave function. So, Laplace transform of f t, since it is a periodic function with period capital T. So, therefore, we can write down 1 minus e power minus s t into 0 to capital T e power minus s t into t dt. So, effectively I have to find the evaluate the integral only, nothing else. So, Laplace transform of f t is equals to, using the earlier theorem whatever we did, using that theorem I can write down 1 by e power minus s into capital T, because capital T is the period of the function, 0 to t e power minus s t into t dt, and very easily you can find out the evaluate the integral with the normal processes, that is normal differentiation under the sign of using integration by parts you can do it. The ultimate result I am writing, this is equals 1 by s square minus t e power minus s t by s into 1 minus e power minus s t. Please recalculate this of your own, just check whether the value of the integral is proper or not. So, you are getting this particular value. If we go back here, your f t is 1 minus this. Here I have given some steps for evaluation of the integral, and at the end I have given the final result. Here 2 minus has come, there will be only 1 minus of this. So, effectively what is happening, I do not have to evaluate the Laplace transform of the periodic function in the normal process. Instead of that, I am just using the theorem and directly writing the formula. Now, let us see the function. We want to find out the Laplace transform of the function where f t is given as 1 when t lies between 0 to 2 and minus 1 when t lies between 2 to 4, and f of t plus 4 equals f t. Please note this one, f of t plus 4 equals f t, that is the function is a periodic function with period 4. So, your formula whenever you will write down Laplace transform of f t, this is equals to 1 by 1 minus e to the power minus t was there. So, it will be e to the power minus 4 s into 0 to 4 e power minus s t into f t dt. This I can write down 1 minus e power minus 4 s. This I can break it, I have to break it into two parts. One is 0 to 2 e power minus s t into f t, the value is 1. So, d t and plus 2 to 4 e power minus s t into value of the function f t is minus 1 into d t. So, I am breaking it into two parts 0 to 2 plus 2 to 4. I can evaluate the integral value of this integral easily. I am just writing the final result 1 minus e power minus 4 s into 1 minus 2 into e power minus twice s by s plus 1 by s plus e power minus 4 s by s. So, this gives the result. Please calculate the value of this one, calculate the value of the integrals and check whether it is proper or not. So, let us come back to this again. Quickly I am showing f t is this minus 4 s. So, that I am breaking it into two parts 0 to 2, 2 to 4. Here I have given some calculations, you can note it of your own, and the final result is given by this one. So, I hope it is clear. Whenever you have the Laplace transform, you have to find out the Laplace transform of a particular periodic function. How to do it? Let us take one more example. Find the Laplace transform of periodic square wave function. What is square wave function? Square wave function we define as f t equals k whenever t lies between 0 to a, and it is minus a whenever f t lies in between a to 2a, that is minus a, and f of t plus 2a equals f t, that is the function is a periodic function with period 2t. Please note this one. This is a periodic function with period 2a. So, in the next slide if you see, Laplace transform of f t will be 1 by e power minus twice a s. Here it is twice a is the period. So, I am writing minus twice a s, and I have to break the function as 0 to a plus a to 2a. One integral will be from 0 to a, another one will be from a to 2a, where 0 to a value of the function is k and a to 2a value of the function is minus k, and this will repeat up to the infinite period. This we have shown in the theorem, and this is the beauty of the theorem of the periodic function. Now, again the rest of the process is the evaluation of the integrals only, and finally, you will obtain this particular result over here. And if you further evaluate this thing, that is from here, this I can just simplify. These are the simplification processes. It is going on simplification of these terms, and ultimately in a very compact form I can write down for this particular function the Laplace transform is k by s into tan hyperbolic a s by 2. So, I hope now from this particular lecture what is initial value problem, what is final value problem, and what is the theorem for finding the Laplace transform of periodic function, that we have studied over here. If required, some more examples we will do in the next lecture.